Okie dokie. Today we are learning three things. Lewis structures. We are going to be drawing resonance structures. And we're also going to be learning something brand new, which you didn't learn in Chem 1, called formal charges. So let's start with some review material here. Starting with the concept of the Lewis dot. Lewis dots are sometimes referred to just symbols of different elements and how the electrons, the valence electrons, are arranged around those elements. So right here, we're going to go ahead first off. We've got the electron configuration here for oxygen. What would be the electron configuration for barium? Help me out because I can't see the table. Xenon, then what? Then what? Thank you. 6s2. I'm glad we just had a test on that. Okay. What a Lewis dot structure is in general, if we're just doing a Lewis dot of an element, you have your element. I'll call it element X. Okay. The element can be surrounded by pairs of electrons, which are valence electrons. You have 4 spots to put electrons. So what are the only types of orbitals that are valence? P and S. So this is kind of convenient. And I'm not like in pre-AP. I don't care where you put the S's. You can put them anywhere. But one side is for S, and then we have 3 p orbitals, right? There we go. And that's how I want you to arrange your electrons. So if you look at something like barium, how many valence electrons does barium have? 2, and they're both in S's, right? So we're going to put them together on one side. Don't care where you put them. I just want them paired. Okay? Now, in a lot of textbooks, especially Chem 1 lower level textbooks, sometimes on the SAT 2 and stuff, you might see barium written as that. I'm not saying it's wrong, but I've seen it both ways, and I prefer it where you have the electrons paired if they're in the s orbital, because it's a more accurate representation of what's going on. Okay? So what happens when we get to O? How many valence electrons do we have for O? 6. So we have 2 in the s, right? And then how many in the p's? 4 in the p's. So we're going to place them singly, just like we did with Hund's rule, in the different orbitals, and then we're going to start pairing them up. And again, I don't care where you put the paired stuff. You can put it anywhere. So that would be the Lewis dot for barium, for oxygen, excuse me. Okay? Now, this is going to make a compound that has ions in it called what? Compounds with ions. Ionic. Very good. Congratulations. Oh, Lord. It's going to be a lot. It's not Friday yet. So, some of you learned in Chem 1, and I'm not going to harp on this. You're never going to see this again. I'm not doing it because it's not a really accurate representation of what process is happening. But we know barium is giving the electrons to oxygen because oxygen is more electronegative, making barium a +2, and then oxygen gets boom, 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 all the electrons, making it a -2. Okay? And how do they bond? Attraction, right? Electrostatic attraction. So Lewis dots typically are not used to represent this ionic situation. We use them to show elements, like the single ones here, and then we use them mainly to draw covalent compounds. And that's what we're going to do from now on, drawing covalent compounds. I will never again have you do the whole transfer electron thing. It's not really what's going on. So go to your next page, and I'm going to introduce or reintroduce, you're going to relearn because you've already done this. I don't care what level of chem you took last year, you did need it available shared. We've made it a Westlake thing, and it's really works really well, where we're going to draw the Lewis structure for these covalent compounds. Notice all of these are covalent. Ionic compounds don't have the central atom with all the atoms around it making certain shapes, because those are all lattices, and they're all crystals. They don't follow any of these rules. So everything I'm doing for the next 4 days, it's about covalent compounds. Okay? So, CCl4. We're going to kind of arrange the atoms now. How do you think the atoms are arranged? What do we always put in the center? Carbon. So we're going to put carbon in the center, and we're going to put chlorine. In all these covalent compounds, there has to be a centralized atom. So don't be trying to make straight lines or weird circles or anything like that. Now, N. N stands for needed. In a perfect world, the total number of electrons that everything needs. everything except, there's some exceptions, but pretty much everything needs what? How many electrons? 8 electrons. There are a couple exceptions. We know that hydrogen and helium they can't fit 8, so how many do they need to be full? 2. And then we've got 2 exceptions, beryllium and boron. Can anyone remember beryllium to be full needs 4. Boron the moron needs 6. I call boron the moron and beryllium psyllium because they're deficient, electron deficient, okay? Both mentally and electronically. I'm kidding about mentally. They're not people. Shocking, I know. So, and then is how many everything totally needs to be full. We've got 5 atoms here that all need 8. So 8 times 5 is 40, and that's what we put there. 8 times 5 is not 35. Thanks, though. Thanks for playing. Next is A. A stands for how many electrons. You can say one of 2 things. Do we actually have or do we have available? That's the number of valence electrons from the periodic table. So carbon has 4. Just look at the group number. Chlorine has 7. 7 times 4 is 28, plus 4 is 32. So how many electrons are we going to share? Subtract, we're going to share 8. That is 4 bonds, because there's 2 electrons per bond. So we're going to place 4 bonds in this picture. There is no arguing with that number that you get, okay? So we have to put in 4 bonds. That's 2, 4, 6, 8 electrons. Of the 32 that we actually have, we've used up 8. How many do we have left to pass around? Math is hard. 24, right? So we're going to place those in pairs, start on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Voila, there it is. Okay? Do y'all remember this? It's good times, good stuff. So let's move on to ClO2 minus. I'm going to throw one in with a minus. What does that minus mean? We have an extra electron. We don't need an extra electron. We have an extra electron available, so where do we put it? Add to the A. I'm talking about a needed, available, shared. We're going to add it to the A, the how many we have available. Okay? So, ClO2, how do I want to arrange it? I want to be as symmetrical as possible. Boom, boom. Okay? Needed, available, shared. How many do I need? Perfect world, everything needs, all of these guys needs 8, right? 8 times 3 is 24. How many do we actually have? Oxygen has 6 times 2, which is 12. Chlorine has 7, which is 19. There's where you know. You're like, that's odd. You can't have share an odd number of electrons, right? So you know you have an issue. Because it's negative, we're going to add an electron and make it 20. So we're going to share 4, and that's 2 bonds. So we're going to put in our 2 bonds. Of the 20 available, we've used 4. So we're going to pass 16 around. 2, 4, 6, go to the outside at first, 8, 10, 12, 14, 16. Now if you look, everybody has 8, right? Everybody's happy. Because it's charged, I'm going to put brackets and the charge on the outside. I'm going to throw, hopefully you have room on your little paper there. I'm just going to throw one more in there. We're going to do NH4+. I want to do something positive for once. Get it? That has lots of deep meaning there. It's been a long day. Okay, NH4. This is what ion? What's this called? Ammonium. All right. So needed, available, shared. How many do we need in a perfect world? Nitrogen needs 8. Each hydrogen needs 2. 2 times 4 is 8, so that's 16. Each nitrogen actually has 5, but hydrogen has 1, so that's 9. What does the plus mean, though? 1 less. So 9 minus 1 is 8. So we're going to share 8 electrons, which is 4 bonds. So 2, 4, 6, 8. Whoa, we've used up all our 8. Of the 8 shared, of the available, we've used them all, and they're all full. Everybody's got 8. Well, hydrogens have got 2. Nitrogen has 8. All is well, right? Okay, we're going to get into drawings where we're going to have some double bonds and some triple bonds. I just want you to know a little bit about their characteristics. We're going to be studying something called hybridization, which is also going to be new in the next few days. And I just want you to see with these models the difference. In a nutshell, you missed it, those of you who are at home, because I had to show some models. A triple bond is strongest, not strongest, strongest and weakest, strongest and shortest due to the overlap of the pi orbitals, or the unhybridized p orbitals in pi bonding. And then the single bond is obviously your weakest and your longest. All right, let's draw some more because drawing's fun. Yay! Carbon dioxide, needed, available, shared. Let's get into the land of double and triple bonds. So if we're drawing this, carbon's going to go in the center. Okay. Now, looking at this, 8 times 3 is 24. Available, carbon is 4 plus 12 is 16, so we're going to share 8. That's 4 bonds. How are we going to place those? 2 double bonds? Really? Okay. I'll do that. Of the 16 available, we've used 8, so we have 8 more to pass around. What if I were to tell you, though, this is an acceptable way as well? Can anyone argue with me about this? It is acceptable. This is something called a resonance structure, and we're going to draw more of these in a second. There is a more stable structure due to formal charges, which is part of our lesson today, but I just wanted to introduce this concept to you. So we can place, we have even a third one here. Look at that. We can place these in multiple ways, and they're all acceptable versions of Lewis dot structures, okay? This is, from what you learned in pre-AP, yes, the more stable, but nobody told you why. They just said, oh, it's symmetrical. I bet you that's what they said, didn't they? Yeah, it's not because it's symmetrical. There's a reason I'm going to show you, okay? We'll get there. Right now we're just drawing. All right, here we have an alkene. When you draw your organic compounds, you can do needed, available, shared if you want. I think, though, carbon and hydrogen chains are almost easier just to draw out because you know carbon makes how many bonds? 4. It has to have 4 bonds, right? So if we have 2 carbons attached, how are we going to place the hydrogens? 2 on each one. Okay. And in order to finish carbon out, what do we need? A double bond. So that's easy enough to do, but I am going to show you that needed, available, shared does work if you decide you don't want to take that path. How many do we need? 8 times 2 is 16, plus 4 times 2 is 8. What's 16 plus 8? 24. Available, we have 4 plus 4, 5, 6, 7, 8. So how many are we going to share? 16. So that is how many bonds? We have more available? 1, 2, 3, 4 plus 8. 12. Math is hard. So that's 12. That's going to be 6 bonds. So I just want to show you that there are 6 bonds in that picture. And so what you would have done, you would have been like, okay, C is attached to C, then I attach all my H's, and you would have realized that that's only 5 bonds, so you need a 6th. So either way you want to do it is fine. Write the Lewis structure for HCN. C's in the middle. I'm just going to leave that puppy right by itself the way, and my board is wigging out on me. Hopefully it'll come back. All right, go ahead and write out HCN. Needed, available, and shared. In a perfect world, how many do we need? 18. Okay. And in what we actually have is 5 plus 4 plus 1 is 10. So we're going to share 8. That's 4 bonds. Where are we going to place the bonds here? 1 and 3. How come I can't do 2 and 2? good. Y'all are so smart. Hydrogen can only bond once, period. End of story. So of the, are we done? Nope. Of the 10 electrons, we've used up 8 in bonds, so we got to take the other 2. Who needs it? Nitrogen. Nice. And that's that. BCl3. Oh, boron the moron. We got to be careful. NAS. Boron is in the center. Cl, Cl, Cl. Perfect world, we need 8 times 3 is 24, but how many does boron need? 6, electron deficient, so that's going to be 30. How many do we actually have available? 7 times 3 is 21 plus 3 is 24. So that's 6 electrons and that's 3 bonds. So 1, 2, 3. Of the 24 electrons, we used up 6, so we're going to place the rest around. So I was at 6, 8, 10, 12, 14, 16, 18, 20, 22. Oh, isn't that nice how that worked out? Is everybody full? Yeah, even boron's full. It only has 6, but it's full. Got it? All right, PF5. Now, this is an exception, and I want to see if anyone can tell me right now without knowing that it's like why that would be an exception. It has an expanded valence. Why are you saying that?
Because it's bonded to 5.
Perfect. It's bonded to 5 things, okay? Being bonded to 5 things means it has to go beyond the 8. Let's pretend you're having a really bad day, though, and you failed to recognize that. And you just started doing needed available shared. That's great. Go ahead. Let's do that. And I'm going to show you what happens when you do needed available shared, and it's an exception. So 8 times 6 is, what is it? 48. All right. Everything has, let's see, 7 times 5 for the fluorines are 35 plus phosphorus's 5 is 40. So we're going to share 8. That means 4 bonds. This is when you're going to realize it's an exception. With phosphorus in the middle, how are you going to attach that with 4 bonds? You can't. When needed, available, shared fails you, boo. You go to the available. And if you need to write these steps down, you can, but here's what you do. You attach everything to the central atom with a single bond. Then you fill up all the outside electrons, and if there's any extra, place them as pairs on the center. So, 40 electrons, here we go. 2, 4, 6, 8, 10. Now go to the outside and start filling those Fs. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, yay, 40. We used up all 40. And again, if there were like 42 or something, we'd take them and we'd place them on the center. But there's not, so let me erase those without killing all my bonds. Ugh, I knew that would happen. Okay? So when needed available shared doesn't work, go to your available, attach everything singly to the center, fill up the outside, and then put pairs on the central atom. I3 minus. Ooh, what's the central atom there? I. That was tough. Okay, needed, available, shared. 8 times 3 is 24. 7 times 3 is 21. Oh, that's odd. Plus an extra electron for the -1 is what? Is that right, guys? 1 bond? So what do we say? We say boo. It's an exception. We cannot connect that with 1 bond. Okay? So what I'm going to have to do is go to the available, connect everything to the center, and then fill out the outer I's. So that's 2, 4 for bonds, 6, 8, 10, 12, 14, 16. Now I take the rest and place them in pairs on the center. 18, 20, 22. There it is. Brackets, -1. So the central atom here, later we're going to have to determine areas of electron density. This central atom has 5 areas. We've got 2 bonds and 3 lone pairs. And that is an expanded valence, right? Because how many is I holding right there? 10. It's holding 10 electrons, so it's an expanded valence, hence the reason we had an exception. Yeah, hand? No? Okay. Okay, now we're going to draw resonance structures. So we're going to start with ozone, and resonance structures are the different possible organizations of bonds, and we have possibilities. Do I do 2 and 2 in carbon dioxide, 3 and 1? Those are resonance structures. So ozone is needed, available, shared. Okay, I'm obviously going to do O attached to O attached to O. Okay, needed is 24. Available is 6 times 3 is 18. How many do we have to share? 6, so that's 3 bonds. So how do I want to place them? 2 and 1, okay? And then whenever there's resonance structures, you draw a double-headed arrow between them. And then I'm going to place it 1 and 2. The bond, that pi bond resonates between the 2 oxygens. So now I do need to fill these up with electrons. I still have 6 electrons to place in every single picture. So 2, 4, no, I have 12, excuse me, not 6. I have 12 electrons to place. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. And there are my 2 resonance structures for ozone. Huge difference in the sneeze there. Any questions on this one? Here we're going to write the Lewis structure and all resonance for the nitrite ion. So needed, available, shared. In a perfect world, we need 24. I can't hear you guys. You're going to have to speak up. Actually, 5 plus 12 is 17 plus 1, 18. So sharing 6. So that's, again, 3 bonds. So we have our N in the center, O, O. This is going to be charged. So we have 2 and 1, and then 1 and 2. And I don't care if you do 2 and 1 and 1 and 2, which one you do first. It doesn't matter. So now we have still 12 electrons to place. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. All right, those are resonance structures. So in these 2 cases, you see how the resonance structures resemble each other? Like that one looks just like the flip of that one. So what we can say, these contribute equally to the hybrid. We call it, that's what we'd say in fancy terms in organic. These make equal contribution to the hybrid. These as well, because they're pretty much, they look like the same molecule. Moving that bond doesn't change much at all. But when you get to something like CO2, you can get some different looking things going on. We end up getting double bonds and triple and single bonds. So we need to be able to determine which resonance structure is actually the most common, the biggest part of the hybrid. The best resonance structures sometimes are 75% there, and then the other ones maybe show up 25% of the time. It varies. But we're going to do that through the use of something called formal charge, and you need to be able to calculate formal charge. This is huge in organic chemistry, which is the next class you guys would take in college, or possibly here with me if you decide to take it next year. So we need to do those resonance structures again of CO2. Do y'all remember what it looked like? We had a double bond O first, and so we had, let's not do that first actually. I'm going to do the single for teaching purposes. I'm going to do the triple single first. So we have a triple single that leaves us 2 electrons there. Okay, is carbon okay? Yeah, carbon's fine, just like that. And then I'm going to do double double. And then I'm going to add on a single triple. Okay, now how do we calculate formal charge? Formal charge is the charge that basically each atom has. It's not really charged because it's the likelihood or it's basically describing the environment that that atom is in. Is it in a very electronegative environment, a very electronic environment or not? To calculate formal charge, don't let this scare you because I'm going to show you a fast way. It's the number of valence electrons minus the lone electrons plus 1/2 bonded electrons. What's cool about formal charge is when you add up the formal charge of all the elements, it's going to equal to the overall charge of the species. Since carbon dioxide has an overall charge of 0, our formal charges will add up to 0. Nitrite on the other page was -1. When we add up all its elements' formal charges, those will come out to be -1. But let's go ahead and calculate formal charge. How you do it is this. I'm going to start with this oxygen right here. What's the number of valence electrons that any oxygen has? 6 minus. Now I go lone pair and half bonded pair. How many electrons are in a bond? 2. So what's every bond then would have, we'd count 1 electron for it. So I'm going to go and count 1, 2, 3, 4, 5. I'm basically counting things around it. That's it. So 6 is valence minus 1, 2, 3, 4, 5. So this has a formal charge of +1 on it. Carbon has how many valence? Any carbon? 4 minus 1, 2, 3, 4. 0. This oxygen, every oxygen has valence of 6 minus 1, 2, 3, 4, 5, 6, 7. So that's -1. Okay, let's go over to the middle one. Oxygen, 6 minus 1, 2, 3, 4, 5, 6. So that's 0. Carbon is 4 minus 1, 2, 3, 4. 0. Oxygen is 6 minus 1, 2, 3, 4, 5, 6. 0. Huh. Maybe that's why that's the best. The best resonance structure that you learned in pre-AP. So this one is 6 minus 1, 2, 3, 4, 5, 6, 7, -1. 4 minus 1, 2, 3, 4, 0. 6 minus 1, 2, 3, 4, 5 is +1. So how do I know which is the best structure? The rules for formal charge are as follows. The compound with formal charges closest to 0 is the best. Or if you have charges, you want the negative formal charges on the most electronegative atoms. Let's see, what is it? Let's kind of think about what it means to be, what formal charge means. Valence is how many electrons an atom is used to having, right? On a daily basis. That's how many I have. Well, subtracting from that is how many electrons it has in a given situation. So if I have a formal charge of 0, it means, hey, I've got the same number of electrons I always have. That's cool. I like that. Okay? But what if I have a negative formal charge? What does that mean? It means I'm forced to have more electrons than I normally do. Well, if that's the case, I better be electronegative, and I better like that. Otherwise, I don't want that formal charge. Okay? Does that kind of make sense? So, which is the best? The middle one. This is going to be the biggest contributor to the hydrogen. This is the most common resonance structure, or the best resonance structure. Resonance. I didn't even spell that anywhere near right. Resonance structure. Okay. I'm going to change this one. Well, no, I'll leave it. C and O. We're going to put C in the middle. N and O. Doesn't matter which you put on what side. Needed, available, shared. We're going to draw all the resonance structures and figure out which one is the best. It says, write the 3 different molecular arrangements and using formal charges, determine the most stable. 8 times 3 is 24. This has 5 plus 4 plus 6 is, oh, plus 1. It is 15. I'm like, whoa, what's wrong? So plus 1, because it is negatively charged, is a 16. So we're going to share 8. How many bonds is that? 4 bonds. Okay, so how do you want to place them? Let's just keep it in order, 3 and 1. And then let's place them 2 and 2. And then, again, those double-headed arrows, I'm not just writing them for grins. Those are resonance arrows. What do those arrows remind you of? Equilibrium. And that's funny because the last time I was at the reading, a professor kind of got all bent out of shape because a student put those arrows on for equilibrium, but he argued that, oh, those are equilibrium arrows and that's a resonance arrow. And it was kind of funny, and we were all like, these are kids, come on, get over it. But anywho, nah. Oh, these guys, we'll put the brackets on them, yeah. And then, oh, actually, no, we're not going to put the brackets on. You know why? Because the brackets tell you the overall charge of the whole molecule, okay? We're writing the individual charges on the elements, so that kind of takes care of that. And one thing I didn't mention, did you see how all these added up to 0? Okay, so all of ours in this case better add up to 1. But I need to place some electrons. I've got 8 to put in every picture, so -1. I can't speak. All of these have to add to -1. And I'm going to make that happen here. We got to add 8 electrons in each picture. So 2 there, 2, 4, 6 there, 4 on each peripheral, 2, 4, 6, and 2. All right. So I don't need to put charge brackets because I'm going to put formal charge on every single element. So N is 5 minus 1, 2, 3, 4, 5 is 0. 4 minus 4 is 0. 6 minus 1, 2, 3, 4, 5, 6, 7 is -1. All right, this middle one. 5 minus 1, 2, 3, 4, 5, 6 is -1. 4 minus 4 is 0. 6 minus 1, 2, 3, 4, 5, 6 is 0. All right, 5 minus 1, 2, 3, 4, 5, 6, 7. Ooh, whoa. 0. 6 minus 1, 2, 3, 4, 5. Wow. Well, looking at this, I can immediately get rid of one of them based on this first rule right here. Which one do you want to get rid of? Third one. These charges are too far from 0. So now we're stuck to choose between these two. Whoops, not that one. This one and this one. Which one do you want? Which one? The one where? This one right here, because the negative is on most electronegative element. The formal charge of carbon is not always 0. There's something in chemistry, in organic, we call a carbocation. In this class, it's going to be 0, but I'm not going to lie to you and say it is. Carbon can have a charge. Doesn't like it, but it can happen. Negative is on most electronegative element. Okay. We're supposed to do one more. So this is SCN minus, if you can't see the minus. It's super duper similar to the one we already drew, so go ahead and get her done. So the formal charge on this S, I'm just going to be writing them down quickly. So 6 minus 5 is 1. This is 0. This is 5 minus 1, 2, 3, 4, 5, 6, 7 is 2. Is that right? 5 minus 1, 2, 3, 4, 5, 6, 7. -2. This is 6 minus 1, 2, 3, 4, 5, 6. 0. 1, 2, 3, 4. It's plus 1, right? 5 minus, oh no, I forgot the 2 bonds, so that's -1. 5 minus 1, 2, 3, 4, 5, 6. So it's -1. And this is 6 minus 1, 2, 3, 4, 5, 6, 7. -1, 0. 1, 2, 3, 4, 5, 0. All right, so looking at this last one, what do y'all think? the middle because -1 on more in this case, that would be nitrogen. So it's crucial you guys practice, practice, practice. You need to do the practice problems in your home